This machine can power an entire city. Inside it, atoms are splitting apart, releasing energy millions of times stronger than chemical reactions. And yet, it doesn't explode. Not today, not tomorrow, not even when things go wrong. In the next few minutes, you'll understand why nuclear reactors, some of the most feared machines ever built, are also some of the most controlled systems in human history. If you enjoy learning how extreme engineering prevents catastrophic failure, subscribe now. This channel exists to explain why the world's most dangerous systems usually don't fail until they do. Let's start with the fear everyone has. When most people hear nuclear reactor, they imagine a bomb waiting to go off. A massive pressure vessel filled with uncontrollable energy. That fear feels logical. Nuclear bombs exist. We've seen what they can do. So the question feels obvious. Why doesn't a nuclear power plant explode like a bomb? The answer begins with understanding what an explosion really is. An explosion isn't just energy. It's energy released faster than anything can contain it. Speed is everything. A nuclear bomb is designed to release its energy almost instantly. The reaction accelerates out of control in microseconds. A nuclear reactor is designed to do the exact opposite. Same physics, opposite behavior. Inside both systems, atoms split through nuclear fission. Neutrons are released. Energy flows outward. But in a bomb, everything is arranged to make that reaction grow as fast as physically possible. In a reactor, everything is designed to slow it down, literally. Neutrons inside a reactor are deliberately slowed using a moderator, usually water. Slow neutrons are easier to control. Fast neutrons are chaos. This single design choice changes everything. The reactor is not racing toward energy release. It's dragging the reaction through resistance. But slowing neutrons is only the first layer of safety. The second layer is control. Inside the reactor core are control rods made from materials that absorb neutrons. When these rods are inserted, they swallow the particles that keep the reaction alive. More rods means less reaction. All rods means no reaction. And here's the key detail most people don't know. These rods are designed to fall into the reactor automatically if anything goes wrong. They don't rely on computers. They don't rely on power. They don't rely on human decisions. Gravity does the job. If electricity is lost, the rods fall. If systems fail, the rods fall. If operators panic, the rods fall. The default state of a nuclear reactor is shutdown. It wants to stop. But even after shutdown, the danger isn't over. This is where the real challenge begins. Heat. After a reactor shuts down, the fuel continues to generate heat through radioactive decay. This is called decay heat. It's weaker than full power, but still dangerous if ignored. If that heat isn't removed, fuel can overheat. Fuel can deform. Fuel can melt. But melting is not exploding. A meltdown is slow. It happens over hours or days, not milliseconds. And reactors are designed to keep removing heat even if everything else fails. Multiple cooling systems exist, each with backups, and backups for those backups. Some systems use pumps. Some rely on gravity-fed water tanks. Some use natural circulation, where hot water rises and cool water falls automatically. No electricity required. No operator input required. Just physics doing the work. Now let's talk about the disasters everyone remembers. Chernobyl. Chernobyl was not a nuclear explosion. It was a steam explosion caused by extreme design flaws and reckless operation. The reactor design had positive feedback, meaning it became more unstable as conditions worsened. That design no longer exists. The failure at Chernobyl didn't prove reactors are uncontrollable. It proved what happens when safety principles are ignored. Now Fukushima. Again, No nuclear explosion. The reactors shut down correctly after the earthquake. The problem came later, when a tsunami destroyed backup power systems. Cooling was lost, fuel overheated. But even then, the reactors did not explode. The failure mode was slow, visible, and studied in detail. Modern reactors are designed specifically to prevent this scenario. This leads to one of the most important concepts in nuclear engineering: negative feedback. As reactor temperature increases, the reaction naturally slows down. Hot water becomes less dense. Less dense water moderates fewer neutrons. Fewer neutrons means less fission. The reactor resists itself. The closer it gets to danger, the harder it pushes back. This is the exact opposite of a bomb. Bombs amplify reactions. Reactors suppress them. And this is why nuclear reactors physically cannot explode like weapons. The fuel isn't enriched enough. The geometry is wrong. The physics won't allow it. Even in the worst imaginable scenario, the reaction cannot accelerate fast enough. The machine simply refuses, which leads to a surprising conclusion. Nuclear reactors are not dangerous because they're unstable. They're dangerous because they demand discipline, maintenance, training, respect for procedures. The real risk is not the machine. It's human behavior around it. That's why modern reactor designs focus so heavily on passive safety. Systems that work without power, without computers, without humans. Engineering that assumes mistakes will happen and survives them. This is why nuclear reactors don't explode, not because they're harmless, but because they are constrained by layers of physics, geometry, and failure-resistant logic. Energy, locked inside rules it cannot break. The most powerful machines ever built, made safe not by strength, but by control.